Hey guys, welcome to my channel. When we need to calculate the value of the definite integral, we can first calculate the indefinite integral of the integrand and then use Newton-Leibniz formula to apply the range of the integral into the solution we need. However, not all functions have elementary antiderivatives. The antiderivatives of some functions are non-elementary. This kind of integral is called non-elementary integral. Here, I need to explain the meaning of non-elementary. If a function cannot be represented by a finite rational operation of power function, exponential function, logarithmic function, trigonometric function, and anti-trigonometric function, or finite composition of them, such a function is non-elementary. For example, factorial functions, ceiling functions, or floor functions are all belong to the category of non-elementary functions. However, not all non-elementary functions have such elegant forms, and many non-elementary functions are even very complex. When the integral of a function is non-elementary function, we usually cannot use the conventional integral method to solve it. For example, the integral sine x over x, or e to the power of minus x squared, and so on, are non-elementary integrals. The specific and common non-elementary integrals have been listed in this box. If you are still not familiar with that, you can press the pause button to review. However, even if the non-elementary integral cannot be calculated by the conventional integral method, some definite integrals can still be obtained by some special methods. Today, I'm going to introduce you to a method for calculating a special definite integral, the integral of e to the power of ax squared. If you want to calculate this one, you need some basis of a simple double integral, just simple. Let's start now. Let's put aside this integral for a while and consider the double integral e to the power of ax squared plus ay squared. Because integral can be transformed into the square of the integral we want, it is observed that the range of this integral is a whole plane. So, for this plane, we can establish both Cartesian coordinate system and polar coordinate system. Let x be r cosine theta, y be r sine theta. Any point in the plane can be represented by radius r and polar angle theta. So, the area element of the original integral becomes r dr d theta. The original integral becomes e to the power of ar squared. Let's now look at the range of integrals. An infinite plane can be both regarded as an infinite square and regarded as an infinite circle. When the size of the whatever this shape is infinite, the boundary of this shape will not exist. Both are equal to the infinite plane. So, we are going to integrate theta from 0 to 2 pi and r from 0 to infinity. Let's calculate the integral with respect to theta firstly, and we get 2 pi times the integral from 0 to infinity, r times e to the power of ar squared dr, right? The rest of the integral can be solved by substitution method. Let's extract the range, and then let the integrand multiply and divided by the dr squared at the same time. We find that dr divided by dr squared is the reciprocal of the derivative of r squared, which is equal to 1 over 2r, just enough to eliminate the above r. So, this integral is pi over a times e to the power of ar squared. By applying the ranging to it, we can get the result we want. It should be noted that the integral converges only when a is greater than 0. Otherwise, the integral tends to infinity. Finally, we can get that the value of this integral is minus pi over a. Because this integral is the square of the integral we want, and the integral we were trying to calculate is greater than 0. Therefore, the value of this integral is equal to the root of minus pi over a. Well, I think that's the end of this video. In the next video, I will continue to introduce another calculation method of non-elementary integral. If you like this video, don't forget to click the like button and subscribe, and you can also turn on the tiny bell. If you have any questions, welcome to leave your comments. In the future, I'll continue to share more interesting mathematical knowledge. Thank you for watching. See you next time. Bye.